Okay. Uh, Honestly, this kind of name is a little bit misleading. Now that I'm reshuffling some stuff around, I see that it wasn't the best name that I could give. But it's okay. We do some stuff that is, in a certain sense, related to linear time invariant systems in the time domain. And next year I will reshuffle. Do not worry. From your side, we still have module by module. So that part has no sense to have a part on that. But the modules that are inside this part are very meaningful, and this one is very meaningful thingy. Because we have been kind of discussing about what is a state, but we didn't formalize it yet, and now we discuss what a state actually is. Prerequisites, I think you know them. And prerequisite learning outcomes, blah 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 blah. Let's go here. Main slides. We want to be able to define in a good way what state is. State is a technical term that shall be used in a, how do you say, meaningful way. You cannot call a state something that is not a state if you want to show the people that you know about control systems. Okay? And it's actually something that is both for linear and nonlinear time dynamical systems. That's why it shouldn't belong to this part here. Honestly, you kind of already know what a state is. The state of the battery of your cell phone is what? Your percentage of the battery right now. True? Because if you know from a time perspective that now you have 67% of battery, and you know that, watch out what I'm doing. This is the state of the battery that is 67%, and you know that from a usage point of view in percentage, how much you are using the phone, you're gonna not use it now, then use it a little bit, then use it a lot. And you would like that kind of to forecast at now plus 7 hours from now. This information, is this information kind of useful for you for doing the prediction? Yes. If you want, knowing right now whether tonight you are going to have at least battery, which information do you need? Where you start and how much you use. Do you see me, people? 1, 2, 3. Do you see me? This information by itself without the usage is not enough. Do you see? And the usage, but without knowing where you start from, also this one is not enough. True? We're together. We need both ingredients. That is going to be the X and the U in the future. So, yeah, it's kind of slightly different. It's before it hits 0%, and I was doing a different example, but we got the point that in a certain sense, to be able to predict, we need some kind of information. Not completely. In a certain sense, I was this one. This one is something that you have a model. This is a model of the system, okay? The model of how fast your battery goes down. True? But you kind of know your cell phone, okay? You might also take into account some external disturbances. True? If it is very warm, very cold. But the intuition is this one. For making forecasts, you kind of need some information. True? And without the information, you are not going to be able to do the forecast. On this, I think we are together. True? 1, 2, 3. Excellent. So let's make a simple model. Time remaining is remaining capacity divided by discharge rate. In a certain sense, I might have this, that is 4 hours, because I've got remaining capacity and discharge rate. This is my X, that is my battery, how much charged. And this is my U, that is how much I'm using it. We are together. Are you seeing the names that they correspond perfectly? In a certain sense, we might rewrite everything as an ODE. Q, remaining battery capacity time. U, current discharge rate. we might have something that is the simplest model, that is this one, an integrator. True? What is a state? This model here highlights state, input, and output. Why? Because the current value of the state, what is a state? A state is a quantity for which the current value of this quantity contains all the information necessary to forecast the future evolution of the output and of the state, assuming that you know U. What is the state of a system from a formal perspective? The state of a system is a vector that we will indicate with X that contains that information necessary to forecast the output, but also the state itself, assuming that you know the state now and the pattern U from now, between now and where you want to predict. To compute the future values Y and X, it is enough to have X and future U. Whenever you have a vector that enables you to do this, that is a state. If you have a vector that doesn't contain enough information to propagate this information and create forecasts, that is not a state. Let's make an example. Go. Read and answer. Read, you have discussed, and answer. Sorry. My fault. State variable is one of the elements of the state vector. So the state vector is all the information that you need. State variable is an information that you need there to be able to do the forecasts. Okay? So the question is basically this one. I should rephrase it. In a spring mass system, to create a model that enables me to do forecasts of position and velocity of the spring, the mass that is attached to the spring. The color of the mass, is it an information that is useful to create a forecast? The displacement of the mass from its equilibrium, is it going to be information that I will need to create the forecast? Yes. Temperature of the spring depends on how sophisticated my model is going to be. True? Because if I do a linear time invariant model, if I do an LTI model of the spring mass system, for this LTI model, this is going to be not. True? But if I do a linear time varying model, this is going to enter. You see? So watch out, very big thingy up to now. Depending on the model that you have, you will have a state vector. Are we together, people? 1, 2, 3. Perfect. Last thing that is very important here. This one, is it a state variable? No one. Because that is the U. There is a signal. There is not a state. It's the U. Think at the battery exercise. That one is how you use the cell phone. True? Remember MPC. How does MPC work? I have now, I have my past Y, I have my past U, and then I'm going to be able to, I have a reference, let's say that this is where I want my system to go, and then if I apply this U, I will get this Y. If I apply this U, I will get this Y. If I apply this U, I will get this Y. True? This is my model that I generate the forecast. Is this one a state? No, this is in a certain sense my optimization variable. You see? Okay? So it's a signal. This is my actuation. This is not going to be my state. My state in a certain sense is the battery charge. And U is the additional information that I need to put inside the, for example, Euler to crank out the forecasts. True? Are we together, people? Excellent. state vector. State vector is all the information that I need to forecast. Go. Read and discuss and tell me. So, what would you say, people? What would you say? Tell me. Fingers up. Everybody's answering 3. Excellent. This one, of course, has no sense. This one, I want to kind of, so the correct one is this one, okay? The correct one is this one, the mass and the velocity, because in a certain sense, think at a position velocity. From position and velocity, you get acceleration. Actually, let's make a model of the spring mass system. We have x2 dot, let's put the m here, acceleration is going to be minus kx minus bx dot, spring and the friction coefficient, plus u, true? Together? So I need state to generate my forecasts. This one, that is here, that is not a state. It's the same thing as before. I'm answering we together because I'm stressing very much this because sometimes it gets confused. Are we together, people? 1, 2, 3. Other questions? No. Okay. So whenever we say modeling a state space dynamical system, from a control perspective, we mean something extremely precise. We mean writing things in this way, where we have a vector, first order, function potentially nonlinear of what? The state itself, the inputs, disturbances, parameters. Think at a logica Volterra. Think at a logica Volterra. Logica Volterra, what do we have? We have we have predators dot is equal, foxes dot is equal to stuff, rabbits dot is equal to stuff. Here we have numbers, true, minus 0.3, plus 7.2, whatever it is. So this theta is the numbers that correspond. The F is the parametric structure, the bilinear model, true? Interesting thing is this one. We always have one dot. Whenever we write in a state space dynamical system, this thing here is the dynamics of the state. So if we have a state vector that is 10-dimensional, it means that we need to have 10 first order, potentially nonlinear, time varying, whatever it is, equations, differential equations. Okay? Together? And then we have another one, another part. What is this part? This part is the output. Let's make an example. If I'm interested in the position of the spring mass system, I'm going to put a sensor that measures the position, true? The Y's is only the stuff for which you have sensors that you measure, okay? So the Y's are the outputs in the sense of the stuff that your supervisory control and data acquisition system, you have sensors to measure stuff, okay? So for example, might be in a tank that you have temperature and volume, and you do not have a sensor for pressure, then you will have Y1 is going to be Y temperature, Y2 is going to be Y volume. You have two sensors or one sensor, I do not know. You have two measurements in your supervisory control and data acquisition system. You've got two equations, okay? Potentially nonlinear, potentially time varying, whatever it is. Important. This one is static. There's no dynamics there. This one is static, dynamic. It's first order. Okay. How much are we together, people? 1, 2, 3. Okay. And then we go to a definition. Number of inputs, number of outputs, number of state variables must be finite. We cannot have an infinite amount of states. Why? Those representations here have been created for implementability not limited. On a computer, you cannot have a state vector that is infinite dimensional. Okay? Together? So, how many first order equations? How many x's there are? How many elements in x there are? And this has to be finite. There are exceptions. There are systems that if we want to model somehow how physics tell us, we might end up with an infinite amount of states. If I have a road and I think at the temperature of the road along the road, how many slices can we make? Infinite. True? It's a partial temperature behavior. Heat transfer. How many of you did some thermodynamics before? I bet everybody has been doing a little bit of thermodynamics. True? If you think at heat propagating in a road, that is a partial differential equation where you've got time but space. You've got derivative in time and derivative in space. So derivative in space, dx dt, or temperature in dx. This stuff here is continuous. We would have an infinite amount of states. You see it? So a PDE by itself would be infinite dimensional stuff. If we want to write as a state space model, we need to do what? Discretization. Okay? Another topic you will see in other places. But you get the point that whenever we talk from a control perspective about state space dynamical systems, those ones are finite objects. We need the state. A state satisfies what we were saying before in Word, something that is called the separation principle. The current value of the state contains all the information necessary to forecast the future evolution of output. The stuff that we were saying before, what is a state? A state is a vector that satisfies the separation principle, what we were saying before. Okay? By memory. You got to memorize this, okay? You're expected to know this by heart. Question.
In non-linear systems, is this with the same ingredients?
The same. Yeah. The same. Think at Lotka Volterra. Lotka Volterra. Does Lotka Volterra representation satisfy this thing here? Very much true. Perfect. Notation, examples of, I don't know. It's the same examples that we are always doing, but somehow we have it. Okay, let's go to a question. Okay, yeah, this one. Yeah, I needed to read it too. Okay, people, what would you say? I do not see. Everybody answers 3. True? Perfect. It's the definition. Okay, people, other questions about this? I think it's very chatty. The important is that you feel that the concept is there. Do you feel that the concept is there? 1, 2, 3. Okay, perfect. Then